Hello, calculus students. I am looking at the part of the notes packet that is entitled Limit Comparison Test. And at the head of these notes is an example problem, actually a warm-up problem. And this warm-up problem is just to see if you're hanging in there with what we've learned so far. So the question is just about this series, the summation of natural log of n over square root of n. I would like you to think through using the roadmap of series convergence and see if you can come up with this answer. So this is not about the new content. This is just a warm-up problem. I'd like you to pause the video, come back, and see how you did. Okay, so if you're coming back thinking, man, that warm-up was a lot, you're right, it is. So if you start at the top of our series convergent flowchart, it would be good practice to at least do a little mental check about the nth term test. Now, sadly, in this particular case, nth term test doesn't give us any information. We end up with a limit of 0. We know that that's inconclusive. Notice that in the midst of my limit question, I noted that I had the form infinity over infinity. So going from my first limit statement to the second one was an application of L'Hopital's rule. Then I thought, well, let's look and see if our terms are getting smaller, because if they're not, I know divergence. So here, I was checking that, and I took a derivative, and I did a lot of algebra work because I was really just trying to get clear on sign, right? I needed to see if my derivative is negative, which would indicate decreasing. And it turns out, with a little factoring, I can think about the fact that square root of x for the domain I'm talking about, certainly, and in general, is going to be a positive, and squaring something is going to make it positive. So the only place to pick up a negative is in this part that has parentheses around it. And that part is going to be negative only if x is greater than e squared, if you just solve that, okay? So this isn't one where it's decreasing from the very get-go, but it ends up decreasing for all the values of x past e squared. So the fact that the first couple kind of tick up, that's not really of concern in the grand scheme of things. We have something that's going to infinity. So this is checking, decreasing. It decreases after the first couple terms. And so between being continuous and decreasing, I know that I can apply my integral test, right? I want to always check those conditions of continuous, positive, decreasing, and I have that well enough that I can use the integral test. So then I'm like, okay, let's use integral test. Well, this integral right here is kind of yucky because I have to use integration by parts. So I wrote an indefinite integral side problem. I didn't want to get into all the limit and bounds and all of that all at once. So I just set up a place where I'm anti-differentiating this. Here's my little pillow substitution box, and I'm doing integration by parts. That is actually, so this is actually kind of mislabeled, right? I wrote this first in my writing. I'm not actually doing the integral test yet. I am just doing an indefinite integral side problem. So I now know the antiderivative I want to use when I do actually get to the integral test. So here is my actual integral test. I set up my integral going to infinity. I rewrite that as a limit because I'm not a sloppy physics student. I use good math notation. And then here is the antiderivative that I figured out previously using integration by parts. And then I'm going to take my limit, and it turns out that this limit goes to infinity. Therefore, I have a divergent series as well. If the integral diverges, that means that the corresponding series has that same behavior, and therefore is also divergent. Now, that warm-up question, that really was pretty extra. So give yourself a pat on the back if you got all the way through that. That's awesome. And now we're going to dive into our new lesson, which is called the limit comparison test. Now, like with a lot of calculus, as you do more problems, you do develop sort of an intuition about a lot of them, right? I know that when we first did U substitution, people were asking, how on earth would I possibly know what U should equal? Well, once you've done several dozen, if not more, of those kinds of questions, you have a good sense of what works well for you. Same with integration by parts. You start to develop sort of an intuition after you've done enough problems. So hopefully by the end of this unit, you will feel the same way about series convergence, that you have some intuition. So these questions look kind of like algebraically more complex than some of the problems that we've done. But something that I kind of have as my gut level feeling is that this first question, because of that, kind of feels to me similar to what happens with our harmonic series. It looks a little bit like this guy. And so I'm thinking maybe it's related to that, okay? Similarly, the algebra of the second problem makes me think that it might be related to another P series that I know about. So, sorry about leaving that up. My dog needs to leave the room instantly. Someone's using the microwave. It's very exciting. So here we have an n squared and we have an n to the fifth. And if you just think about, the rest of it is there. I'm not saying it's, we should just completely disregard it, but those are the dominant parts of the top and of the bottom respectively. And so if we just think about sort of like a degree idea, this maybe is going to act something like 1 over n to the third, maybe. And that intuition serves us very, very well for questions that that we're going to use the comparison test on. Like the integral test is like fine, but to be honest, it sort of can be awful, right? Like if I had a series like 1 over 3 to the n plus n, like I am not going to want to integrate that. That has like a base that is 3, and I have to remember like where does this natural log thing go or something like that, and how am I even going to deal with the plus n? Like integral test has its purpose, you guys. Like there are times that you have a series that corresponds nicely to a friendly integral, but there are awful lot of times that you have something that is horrific to integrate, okay? Or maybe your conditions aren't met. So here is a test that I actually love. I arm wrestled Covey to be the person who got to do this video because I like limit comparison test that much. I think he let me win the arm wrestling. Okay, so given two positive series, so note here that we do need to have terms that are positive, and you have to have two different series. So there's one that is the problem you're doing, and then there's another that is one that you know. Okay, so there's one series that is a problem that I'm being asked about. The one that I know is most likely going to be something that I would think about with a P series, because as I mentioned to you at the end of the integral test video where we talked about P series are super easy to just discern, right? You just have to say, like, am I in the case of, being less than one or more than one? Which case am I in, right? With one being the tipping point. Harmonic series, divergent, okay? So you have to have a series that you know and a series that you want to know about. And then what you do is you just take the formula part of each of these, put them in a ratio, and assess that limit. Now, if the result of that limit question is something, okay, now there's like a cool math lingo here. This guy means is an element of. Right? And then this guy, if you wrote it in like handwriting, it usually looks like this. And that means real numbers. And with a little plus, it means the positive real numbers. Okay? So the positive real number is an element of the positive real numbers. So if the result of this limit question is something, some value, that is an element of the positive reals. So in other words, it is not infinite, okay? We want to have something that is both positive and finite. If that is our result, then either both series converge or both diverge. So they behave the same is the result. Now notice that this does not say, not say that if I get infinity, that means they behave differently. It literally says only what it says. So the limit comparison test is conclusive when you have a finite limit. If you have a finite limit, positive and finite limit, then the series behave the same. So if you're looking at your flow chart, this is zeroed in on where the limit comparison test is here. The positive part is this greater than 0. The letter L should indicate to you that there is a limit, right? When we write limit of blah equals infinity, that's really a very confusing statement. This is describing why the limit doesn't exist. Okay, limits themselves are finite values. So this is actually sort of like a non-limit. Sometimes people call this a descriptive limit. I think we should call it a descriptive non-limit. You're describing why the limit doesn't exist because there's not a finite value, okay? So this is actually not a limit. Here we are assuming L is like a finite value, okay? All right, so let's start looking at some together, okay? So this first guy says investigate that problem, right? We had these at the beginning, right? These were the 2 questions I was looking at back here. So let's take a look at this guy. Let's try to utilize limit comparison test. Now, what do I know about this? I know that it's divergent, right? Because it's a P series with P equal to 1, and it even is so famous it has its own name. It's called the harmonic series. Okay, so I'm going to try limit comparison test. Always good to label what you're doing. So I'm going to take the limit, and now let's think about which way would be most advantageous to divide. Let's go this way. And I think in a second, if you don't already, you'll see why I did it in that order. So it didn't say back here, like which one to put on top, which one to put on bottom per se, right? Okay, so if I'm dividing by fractions, I'm multiplying by the reciprocal. And I get this. Now, why is that helpful? Well, guys, because you can do one of these, whereas if it were flipped over, could I do one of those? I could not. Okay, so you always want to end up with like the more complicated thing upstairs, if that makes sense. Okay, I'm going to do a little monomial in the denominator, a little monom-denom right there. These ends go away. Okay, the pen lost me for a second because I bumped things. Okay, so those ends cancel, and then I have 3 plus, and then 4 over n. 4 over a huge thing is going to go to a small thing, and so here I get 3, and 3 is a member of the positive real numbers, and so I'm going to write some English now. I highly advise the English, okay? So because I know that this series diverges, this series that I was given also diverges by the limit comparison test. Okay, I've clearly shown here that I am checking this end condition, right? You need to have this part. Okay, so I am clearly stating that as part of my work, and then I wrote this nice sentence. That seems like a really, really good idea, okay? And I have the word diverges here, so my answer is clear. Okay, I am going to come back to that other question from the start, but not quite yet. So the second example is this one, and hopefully you can see if you kind of strip away the extra elements of this, it's going to be similar, maybe, I think, to the P series with P equal to 2. So we'll compare to this P series, which converges because it's a P series with P equal to 2. Okay, notice that I really want to lay out my thinking. These are like little proofs. Proofs, yes, I did say proof. You don't have to write 2 columns to have it be a proof. Okay, so we're going to do limit comparison test. And so I'll have the limit. Okay, let's think about how I want to do this. I want this simple guy here, and I want my actual problem here. So the big thing ends up being on top when I divide. So I'll have the limit of this over n squared. We can do a little division action here and have the limit of 4 plus 2 over n plus 5 over n squared. If I split that up, and then as I take that limit, I get the answer of 4, which is an element of the positive real numbers. Okay, so then I want to conclude that with a beautiful sentence. Okay, now the conclusion is that this problem that I'm looking at, right, the problem that was stated to me versus this guy that I brought into the question and did the limit comparison test on, the conclusion is that they behave the same. And the original was a convergent series, so that means that this also is a convergent series. Okay, so I want to clearly state my reasoning, right? I want to include this comparison part, right? Like the, condition of the test. I want to make sure I clearly say converges or diverges. I want to make sure that I can explain how I knew about the one that I'm using in the comparison. Okay, so there are 3 more questions coming up in your notes, and these I think you can certainly do 3 and 4 on your own. So let's have you do that and then come back and we'll do 5 together. Okay, so 3 and 4, pause the video and then come back and check 3 and 4. Okay, try 3 and 4 alone. Okay, let's take a look at the solution to number 3. I hope you tried it by yourself first. So here's my solution to number 3. I thought that what it looked like if I stripped away sort of the extra stuff is it kind of looked like 1 over square root of n. And 1 over square root of n is a p-series, and it's a divergent p-series. Okay, so it does turn out that I get a positive real number. So that means that they have to behave the same. And since the series I was using to compare to is divergent, that means this one is also divergent. Okay, remember that you have to think about the behavior of the thing that you're comparing in the limit, right? And this one that I just highlighted as a series would be a divergent p-series. So the fact that I got a real result, a positive real result, means they behave the same. Same in this case means divergent. All right, question 4. This is the other one that was mentioned at the beginning of the lesson. And so it looks most like 1 over n to the third. Now, if you think about this guy as a p-series, that's p equal to 3. So that's going to be convergent. And so as we work through this, we do get a positive real result from the limit. So that means that they behave the same. This given series is going to act the same way that the sum of 1 over n cubed acts. And that is convergent, so 2 is this one. Okay, so those 2 are kind of right down Main Street questions. Hopefully that went well. If not, please reach out for some help. But this next one is a little bit more sticky, just because I'm not really sure, like I don't think I can just make this a p-series. This is a pretty dominant trait right here, having this exponential. So I look at this and I see that 2 to the n, I think that's going to be like too big to ignore. And then I see this part, the n over n cubed, and that's sort of like having n squared in the denominator. So I would say the 2 to the n on the top and the n squared on the bottom are the things that really are sealing this. The 3 as a multiplier and the adding 4 are not really of consequence. So really, if I'm going to use 2 to the n over n squared in a limit comparison, I need to first figure out how that guy acts. It's not just a p-series. Okay, so forgive my poor handwriting here, but this is the question that I'm wondering. I'm wondering if this possibly related series is convergent or divergent. So with this guy, I'm going to go through my flowchart steps. I'm going to think about nth term test. So I'm going to look at this limit. Okay, now what is it that I'm doing here? Can you tell from the blue to the red? Using L'Hopital's rule, that's right. So I have an infinity over infinity situation, If this were my AP test, I would write my 3 bullet points out. Here, I am trying to figure out my derivative. Or actually, I figured out the derivative of the top, derivative of the bottom. I'm trying to find my limit. I apologize for misspeaking there. And then I'm doing a little algebra step. So this 2 will take away one of these 2. So that's why my exponent changed a little bit. I just realized I misspoke. That wasn't just an algebra move. I was doing L'Hopital's rule again. I apologize. But in any case, however you get there, you should find out that this limit does not approach something specific. It just keeps growing. So we have a divergent relative, a divergent relative. So now when I come to the limit comparison test, I'm using this cleaner version, right? The thing I was just looking at that I just figured out was divergent. And I have here the thing that we are actually trying to consider, right? That we're trying to sort out. And so I'm going to do some algebra moves now and try to get this to boil down to something I recognize, okay? Okay, so just rewriting the division as multiplication, we come to this point, and then I have a 2 to the n, that will cancel, and then I can rewrite this as 3n cubed plus 4 over n to the third, and this is looking so much better. And I can split this up, right? Think about the limit as n goes to infinity. So as that denominator gets larger, 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 that second piece gets smaller, smaller, smaller. And I have 3, which is indeed a positive real number. So that means that these 2 series, the one that's on the top here, so this series and this series, the one that was in the question, must behave the same way. How did this one behave? It was divergent. So that means that this other one is also divergent. And we should conclude our work on this with a nice sentence, something along these lines, right? Because the one I was using as my comparison was divergent and reason, then the one that I'm looking at also diverges, also behaves the same way due to limit comparison test. Okay, at the very end of your notes, I have 3 problems that are written not in sigma notation. So this is a little blast from the past of how do you write things in general, in generalized terms or in sigma notation. So I have 3 series here. I would like you to work on writing them using sigma notation. I recommend that you number each of these, right? So I want a formula where I put in 1, I get 3 on the top and 4 on the bottom. I want a formula where if I put in 2, I get 5 on the top and 9 on the bottom, okay? I recommend not just looking for patterns side to side. Those aren't generally as helpful as looking from the position to the pieces of the term, though I just highlighted the denominators because there's something interesting there. And I'm highlighting the numerators because there's something interesting there, right? The denominators are all squares, perfect squares. The tops are all odds. That's interesting, okay? So what I'd like you to work on is to write sigma notation for these 3 series as best as you can. And when you come to class, we're going to pick up right from here. We're going to discuss what the series notation is for each of these 3 problems, and then I will have you do limit comparison test on each of those 3 series as written in sigma notation. Okay? Thank you very much for getting through this lesson with me, especially that beastly warm-up. Hang in there, you guys. We're almost through the finish line of all of your calculus. Okay? Thanks. Bye.